In 2020, global plastic production reached 367 million tons. Of that, an estimated 14 million tons are discharged into aquatic environments every single year. While oceanic accumulation dominates public discourse, inland hydrology reveals a highly concentrated issue. Lacustrine systems, freshwater lakes, are accumulating microplastics at vastly accelerated rates compared to oceans. The data from highly developed watersheds is stark. In China's Lake Poyang, researchers have recorded concentrations up to 34,000 microplastic particles per cubic meter. We see similar spatial density in northern Italy. Lakes Maggiore, Iseo, and Garda exhibit surface distributions ranging from 25,000 to 39,000 microplastics per square kilometer. Smaller-scale studies in India, mapping Lake Renuka and Red Hills Lake, confirm this is a ubiquitous phenomenon affecting water bodies of all sizes. The extreme concentration in these lakes is a direct function of proximity. Unlike oceans, which benefit from massive spatial buffering and dilution, lakes exist in immediate contact with human infrastructure, receiving concentrated runoff with nowhere else to go. Unlike flow-through rivers, lakes are constrained basins. They act as terminal accumulators for wastewater, stormwater, industrial discharge, and atmospheric deposition. These vectors pump in complex synthetic polymers that disperse unevenly, some floating, others sinking straight to the bottom. To deconstruct this accumulation, water resource engineers must map the specific emission vectors, the morphological profiles of the particles, and the exact polymer density of the contaminants. Every urban lake operates as a closed-loop terminal accumulator, capturing the exact footprint of its watershed. This containment effect explains why urban lakes face much higher microplastic concentrations than remote alpine or rural lakes. The exposure is immediate and high volume. The primary driver of this contamination presents an engineering paradox. Wastewater treatment plants operate with extremely high efficiency, filtering between 88 and 99.9% of microplastics. Yet they remain one of the largest single pollution vectors. The sheer, continuous volume of treated effluent completely overwhelms that high percentage of filtration efficiency. The majority of the microplastics slipping through this municipal filtration originate directly from domestic and industrial textile laundering. The emission data is highly specific. Washing just 5 kilograms of polyester cloth can release approximately 6 million individual microfibers into the wastewater stream. Even organic and synthetic blends contribute heavily. A single wool item can still produce up to 110,000 fibers per wash cycle. Current municipal filtration technology simply cannot offset the exponential volume of synthetic shedding occurring daily at the consumer level. Beyond treated effluent, urban stormwater acts as a direct bypass vector, carrying untreated surface pollutants straight into lacustrine systems during heavy rainfall. Tire wear particles are a massive contributor to this runoff. Nearly 11,000 tons of synthetic tire particles enter surface waters from German highways annually. Recreational infrastructure, specifically artificial turf and synthetic sports facilities, also represents a substantial and frequently overlooked source of these stormwater microplastics. In suburban and rural lakes, the primary input vectors shift. Infrastructure runoff decreases, replaced by direct contamination from agricultural applications and degraded fishing gear. The diverse land use across a watershed acts as a customized blueprint. The activities happening on the surface directly dictate the specific polymer profile of the receiving lake. We can read this profile by analyzing the physical shape and size of the particles. In surface waters, microplastics are predominantly under 1 millimeter, while those bound in sediment are typically under 0.5 millimeter. Researchers currently classify these suspended particles into 4 primary morphological categories for analysis: fibers, fragments, films, and foams. Comparing morphological breakdowns across global lakes provides a fingerprint of local pollution vectors. China's Lake Wabu shows a mixed profile, 53.7% fibers and 32.6% fragments, indicating blended wastewater and industrial influx. Conversely, Italy's Lake Bagno dell'Acqua shows an extreme 89% fiber dominance, indicating heavy domestic wastewater. In Africa's Lake Victoria, 90% of the fiber morphology is directly traced back to abandoned polyethylene and polypropylene fishing gear used by local industries. Morphological analysis transforms lacustrine plastic pollution into a forensic ledger of local human activity specific to each individual basin. Beyond their physical shape, we have to examine the fundamental chemical composition of these particles. Across global lacustrine environments, polypropylene and polyethylene account for the vast majority of all detected polymers, representing over 72% of the total volume. Secondary polymers frequently detected include polyethylene terephthalate, or PET, at 18%, along with polystyrene. This chart illustrates density stratification within a water column. Freshwater's specific gravity is exactly 1.0. A polymer's relative density determines its fate. Low-density polymers like polyethylene and polypropylene, with gravities below 1.0, actively rise and cluster at the surface level. This surface accumulation directly impacts the pelagic zones, exposing surface-feeding fish and zooplankton to high concentrations of floating debris. Conversely, high-density polymers such as PET and PVC have specific gravities greater than 1.0. These particles sink rapidly past the freshwater baseline. This sinking mechanism deposits massive concentrations of microplastics straight into benthic sediments, heavily exposing bottom-dwelling macroinvertebrates. Spatial distribution is further complicated by environmental biofouling. Microorganisms adhere to floating plastics over time, increasing their density until they eventually sink to the bottom. Density acts as the primary spatial sorting mechanism in a lake. It turns the water column into a stratified filter, dictating exactly which ecological niches will be exposed to specific types of polymers. Track the theoretical journey of a single microplastic fiber from effluent discharge to its deposition in the sediment, and a secondary threat profile emerges. This deposition introduces a dual threat profile, combining the physical risks of ingestion with the pervasive danger of chemical exposure. Commercial plastics are manufactured with integrated chemical additives. Plasticizers, UV blockers, and flame retardants slowly leach from the degrading plastic directly into the surrounding water. Furthermore, the rough, degraded surface area of these microplastics creates a vector effect. They actively absorb polycyclic aromatic hydrocarbons and heavy metals from the surrounding environment. These particles function as active, highly efficient delivery vectors, transporting concentrated environmental toxins directly into the lacustrine food web. The concentration of microplastics in any given lake is not a random occurrence. It is a predictable mathematical function of its watershed infrastructure, topography, and hydrodynamics. Standard environmental assessments that only measure the top-line microplastic concentration are insufficient for modern water resource engineering. Universal morphological and chemical fingerprinting must become standard methodology. We have to map the exact chemical breakdown back to the watershed's topographic layout. This high-resolution data allows municipalities to target precise, source-based interventions. Rather than attempting a generalized, basin-wide cleanup, engineers can deploy specialized wastewater retrofits for microfibers or targeted stormwater traps for tire wear. By understanding the physical and chemical mechanics of lacustrine sinks, we can transform lakes into forensic diagnostic tools for managing the human footprint.